Hello, my name is Touma. My ID is 6359553, and this is the second lab report from Group 2.
Hello, my name is Mohammed.
Charge of creating the actual circuit with all the conditions set, and also to answer the first question. The objective of the first question is to determine if the Kirchhoff's voltage law and current law are true based on the circuit that I created. So here, in the first condition, R1 had to be bigger or equal to 1 kilo ohm, which is true, I made it 1 kilo ohm. R2 had to be greater or equal to R1, I made them equal. R3 had to be bigger than 2.2 kilo ohms and smaller than 10 kilo ohms, and I made it 3 kilo ohms, so it's also true. R4 had to be bigger or equal to 470 ohms and smaller than 100 kilo ohms, which is also true as I made it 10 kilo ohms. And the first voltage had to be in between 2 and 7 volts. I made it 5. And the second voltage had to be between 1 and 20 volts, which is also true. So all the conditions are met. So this brings us to the first part of the question, which is verifying both laws, the current and the voltage laws. So first, for the current law, it states that the sum of incoming currents at a node is equal to the sum of outgoing currents at that node. So as you can see in the previous slide of the circuit, the current of R1, R2, and R3 are stated, as you can see, is 2 milliamps, 1 milliamp, and 1 milliamp, corresponding to the three resistances, and the outgoing has to be equal to the incoming. So I made it an equation, and I put IR1 equal to IR2 plus IR3, which in this case is equal, because it will be like 2 equal to 1 plus 1. So the current law is true for this circuit. And then the Kirchhoff's voltage law states that the sum of all voltages in a loop is equal to 0. So I took the loop of R1, R2, and R4 for this example. To get the voltage in R1, I subtracted V1 minus V, which is 5 minus 3, which gives out 2 volts. For the second resistance, it was V minus 2 minus V2, which was 3 minus 2, 1 volt. And then for the last one, V2 minus V1, so 2 minus 5 minus 3. If you add the 3 together, you get 0. So this law is also true. The condition that I got from this laws is that the conservation of energy is true for the circuit, and also the charge conservations. We can see that they are true for the circuit as well.
Hello, I did question 1 with part 2 and part 3. My teammate did part 1 and the circuit drawing of the circuit. So basically in part number 2, we have to find the power absorbed by R3, and by doing that, you just get the voltage and you multiply it times the current 1 minus current 2. And with that, I got 0.004285 amps. I'm not sure I did it correctly just because this number seems quite low, and yeah, but these are the numbers that were provided by my teammates, so that's what I went with. Um, I for part 3 of question number 1, I did the current through the resistors, and this is pretty straightforward. You for R1 you do the current 1 minus current 3, and then I got 1 over 1000 amps. Then we do resistor number 2, that you do current number 2 minus current number 3. I got 0 amps. And then for resistor number 3, I did current number 1 minus current number 2, which is 1 over 1000 amps. And then resistor number 4, sorry, is just current number 3, which is 1 over 1000 amps. All these numbers were provided by my teammate, the currents, and they were in mega amps, and I just converted it to amps at the end. And then we have the second part of question number 3, which is the voltage across the resistors. And to do that, you just do V1 minus V, which is 5 minus the 4.2857. which gives us 0.7314. And then, well, it's pretty straightforward. It's all there. Then you do V2 minus V, and then it would be 2 minus 4.2857, which gives us negative 2.2857. And then for V, it's just the regular voltage that we got. And then V1 minus V2, which is 5 minus 3, which is 5 minus 2, which is 3. And also for the voltage that I got, I kind of had to do part 1 again, just because I had to get the voltage and that wasn't provided by my team members. So I kind of just did it myself. I'm not sure if I did it correctly, but I got the 4.2875 V, and that's where I got the V from. It's up here. But yeah, thank you.
Hello, my name is Mohammed. This is lab 3. This is the work that I did for the part 2. As you can see, when you simplify it, complete changes. This is what I got for the first part. This is for the second part. And over here, this is the superposition theorem. And as you can see, it is used extensively to analyze and solve complex electrical circuits, and allows us to simplify the circuits by breaking it down into smaller, more manageable parts, and then combining the results to find out the total behavior of the system.